Let's get started. Hello, everyone. Welcome to the theory seminar. I'm very happy to introduce our speaker today, Shivam Nadimpalli. He's currently a postdoc at MIT, where he does research in classical as well as quantum complexity theory, high-dimensional geometry, and property testing. He earned his PhD from Columbia under the supervision of Rocco Cerveto and Michalis Yanakakis, and before that he did his undergrad at Brown, where he did an honors thesis with Sorin, and in Sorin's words, he's an amazingly talented researcher, one of the top three most brilliant undergrads he has worked with in his 20 years at Brown. And today he's going to tell us about Gaussian polytope approximation. So without further ado, let's welcome Shivam.
I think we ran into a technical issue just as the intro ended, but awesome. But yeah, thanks Behan for the introduction. Thanks Soren for the kind words. It's really nice being back here. I spent a lot of time in the CIT as an undergrad, so it's always good to be back. And I'm going to tell you about some joint work with Anindya Dey, who's at UPenn, and my advisor, Rocco Cerveto at Columbia. And even though it may not seem like it, this talks about complexity theory, even though it seems like there's nothing to do with complexity at first sight. So in a sense, CS 1010 is to thank for this talk. But if you don't like it, then Columbia should get all the blame. So let me get started. This is a talk about polytope approximation, and more broadly, it's about convex geometry. So we're going to be interested in convex subsets of high-dimensional Euclidean space. So again, our n is just going to be our high-dimensional setting. Think of n as a very large number, and we're going to be interested in convex subsets of this of Euclidean space. Again, convexity is a very basic natural geometric property. It shows up everywhere. In high dimensions, often you assume convexity to do optimization, learning, various algorithmic tasks. And it's also just a very nice and simple geometric property. So just to make sure everyone knows what convexity means, a region is convex if for any 2 points in the region, the line connecting the 2 points is entirely within that region. So this is a convex set. And maybe the first thing you learn about convex sets is that they have supporting hyperplanes. So in this two-dimensional picture, if you pick any point on the boundary of this set, you have a hyperplane, which in 2 dimensions is just a line, which separates this convex set. So this convex set lies entirely on one side of this hyperplane. And you can do this for every point on the boundary of the set. And if you intersect all of these hyperplanes, these purple regions, you just recover the set itself. So the first fact about convex sets that we learn in maybe even in algorithms when you're doing linear programming or something of that sort, is that every convex set can be written as an intersection of possibly infinitely many half spaces. So in 2 dimensions, a half space was a line. In n dimensions, it's going to be an n-1 dimensional surface defined by a linear form. Yeah. And it's easy to see that in order to write down a convex set exactly as an intersection of half spaces, you might need infinitely many. Right? Just for the circle from the previous diagram, you really have to put down a half space at every point on the boundary in order to write it down as an intersection of half spaces. Question? Yeah. So VI is a unit vector. So in this picture, let's say VI is like the unit vector pointing along the x direction, and theta I would be the width of this half space along that direction. Does that make sense? Yeah. So good question. VI's are going to be unit vectors. Theta i's are just how far the convex set extends in that direction. Yes, so like I was saying, you need infinitely many to represent convex sets, but infinity is a big number, so let's try to settle for an approximation. So going back to this picture, let's say you put down a few more half spaces, and then you get lazy and decide to stop. Then it's natural to maybe settle for this intersection of 6 half spaces, this hexagon, as kind of a good enough approximation to this original set K. And the set L does a pretty good job at like, correctly predicting what K does, except on this red region. And you don't just, you can also just ask about arbitrary approximators, like not just approximators where the faces touch the convex set, but you could have the faces intersect the convex set as well. So again, in this set L prime, the error region is this red region. But in order to be able to talk about the quality of an approximator, you need to have some way to measure the distance between two sets in high dimensions. And arguably the simplest thing to do, and something which is actually used throughout theoretical computer science and math, is to use the so-called Gaussian distance. So given two sets in Rn, the Gaussian distance is just the probability of a standard Gaussian random vector landing in the error region. Yeah, so we know the Gaussian, we love the Gaussian. It's always going to be a standard Gaussian, so the mean's always 0 and the covariance is the identity. The covariance matrix is the identity matrix. This is a very natural, well-studied measure, like distance metric in computer science. Any questions about this distance metric?
What if K and L are not near the origin?
Awesome. So I think U is kind of getting at the point that this distance metric is not translation invariant. So if you take a set and you send it far away from the origin, then it's, the probability of a Gaussian landing in it is 0. So it's really close to the 0 set. So in some sense, this is not a translation invariant distance metric. It's not a scale invariant distance metric either. These are good points to keep in mind. Good. So I'll get to that in a little bit as well. But Gaussians and convexity show up. Like the short answer is that they show up in like other areas, like in discrepancy theory and a bunch of places. So there's lots of reason to study this, and I'll give a concrete example in like a few slides. Right, so just to kind of connect this definition to the pictures from the previous slide, the distance between K and this hexagon is the probability of a Gaussian landing in this error region. And same thing for K and this L prime. Yeah? And so kind of the concrete question we're asking in this work is the following. Let's say someone walks up to you with a convex set and some error parameter epsilon. How many half spaces do you need to approximate it to accuracy to error epsilon under the Gaussian distance? So this is the question that we're going to be interested in. I'm not going to care about epsilon dependence. I'm going to set it to some fixed constant for the rest of the talk. So it's always going to be 0.1. Okay? And we're going to be interested in both upper bounds and lower bounds. So by upper bounds, I mean positive results to approximate generic convex sets. And by lower bounds, I mean explicit constructions of convex sets, which are hard to approximate, which need a large number of half spaces to approximate. So coming back to Pehan's question, why are we thinking about Gaussian distance? Well, it turns out that pretty much every other distance metric you can think of has been studied. In some sense, like this question of approximating convex sets by polytopes is like 2,000 years old, because this is how we learn to compute the area in like 5th grade or whatever, right? You approximate the circle with the polygon, and then you increase the number of faces to infinity. But pretty much every other distance metric you can think of has been studied by the mathematical community, and we have a really good understanding of upper and lower bounds for all these other distance metrics. But within computer science, we actually care a lot about the Gaussian, because a lot of computational tasks, like learning, estimation, and like distribution testing types of problems, become efficient. You get efficient algorithms for these algorithmic tasks when you assume convexity. And in fact, the starting point for this work is this classic result of Clivens, O'Donnell, and Cervedio from 2008 on learning convex sets under the Gaussian distribution. So I'm going to tell you a little bit about this result, which is like how we got started on this problem. This problem of learning convex sets is the following. You have an unknown convex set, so you don't see the set K, but instead you see a black box or a blue box, which you can query membership in K on. So you can feed it a point X, and it tells you if it's in the set or not in the set. So let's say you fed it that point, and it tells you it's in the set. that point's not in the set. And you can draw a bunch of samples, and you want to output an approximation to the set K. Right? So let's say you've only seen these samples. Again, remember, you can't see this faded out convex set in the background. Your goal is just to output an approximation under the Gaussian distance. And this nice result of Clivens, O'Donnell, and Servedio tells you that you could do this with sub-exponential sample complexity. So n to the root n samples are necessary and sufficient for this problem. Okay? This is awesome, and like their proof uses Fourier analysis and like nice results from convex geometry. But one thing which is annoying about their result is that they output a polynomial. So their approximating set, it's like this squiggly high-dimensional polynomial, but it's not a convex set. There's no reason for it to be convex. So you're trying to learn convex sets using non-convex hypotheses. So in particular, this is an improper learner. And kind of the starting point for this work was, well, what if you want to learn convex sets using convex sets? And arguably, the simplest class of convex sets is intersections of half spaces. So this was kind of how we got started on this question. Hopefully, that's making sense. And stop me and ask me questions if not. Behanya. N is the dimension. Yeah. So all the sets are in Rn. Yeah. Awesome. So the goal is to like build towards proper learning for convex sets. So learning convex sets using convex sets. And so that's how we got started on this question of Gaussian polytope approximation, which is, again, how many half spaces do you need to approximate a convex set K under the Gaussian distribution? And like I said, we want upper and lower bounds. And I'm going to start by telling you the upper bound we prove. It's not too surprising if you've worked in high-dimensional geometry before. This is going to be the only proof in the talk. The rest of the talk is going to be pictures. But hopefully that's okay. So we show that an exponential number of half spaces suffice to approximate any convex set to accuracy 0.1. Okay, so 2 to the n. The O tilde is hiding like a logarithmic factor or polylogarithmic factor, but we don't care about that. So here's the proof. It's back. Oh, great. So is it because I'm moving?
Yes.
Okay, huh. That's strange. Okay. Oh no.
An activity issue.
Yeah. Oh, I think it's back. Yeah. Okay. I'm going to try not to move.
Very far away from you.
Okay, good. This side, thanks. Yeah. Yeah. Awesome. So it's going to be the only proof. So in case you forgot what we're trying to prove, we're trying to show that an exponential number of half spaces are enough to approximate any convex set to error 0.1. Okay, great. So I'm gonna give you a proof sketch of this, and it's the only proof in the talk. So let's say here's a set K that you want to approximate. The first thing you can do is you can intersect it with a ball of radius root n plus 100. This is just an L2 ball. This is because just by basic concentration of measure, just the concentration of the high-dimensional Gaussian, you can show that the amount of the probability of a Gaussian landing outside this ball is like 0.005 or something. So just a chi-squared tail bound, just a basic tail bound, will tell you that the probability of a Gaussian landing having 2 norm greater than root n plus 100 is going to be 0.05. So we're going to happily give up on everything outside this ball. We only care about action within this ball. So let's intersect the set K with this ball. So you end up with this weird set, which I'll call K prime. And our goal is to get a 0.05 approximator to this set K prime. because we already ate 0.05 error on the outside. If you eat 0.05 error over here, then add them up. Triangular inequality tells you that you've in total you've eaten 0.1 error, which is our goal. So and this is going to be my notation for the L2 ball. So the distance metric is the L2 norm of radius root n plus 100. Yeah. Great. And like I said, I'm going to call this intersect with set k prime. So so since the goal is to get a 0.05 approximation to this new set k prime, we can actually use an off-the-shelf result from the 70s due to Dudley as well as Bronstein and Ivanov, which tells you that there is an exponential facet polytope which approximates the set k prime under this distance metric, which is just the following. It just tells you that the maximum distance of your approximating set L to a point in k prime is going to be 1 over n to the 1/4. Yeah. So in pictures, what this result of Dudley and folks is telling us is that if you have the set k prime, then there exists an approximator of 2 to the order n half spaces, such that the distance between any point on this approximator L and this target set k prime is like 1 over n to the 1/4. This 1 over n to the 1/4 might seem mysterious, but I'll tell you why we need that in just a second. But is this picture making sense to everyone? I see people nodding, but yeah? Good. So this is giving you an approximator in terms of this weird distance metric, but we're after an approximator under the Gaussian distance, right? We want to control the probability for Gaussian landing in this red region. And so one thing you could do is you take that little red strand and you slide it across the boundary of the set k. So you end up with this dotted set. This is kind of like the enlargement of k prime to include all the points which are distance at most that much from k prime. And just convexity tells you that the probability, the error region we were trying to control is upper bounded by this purple or blue region, okay? And this is much easier to analyze in some sense. So I'm just gonna rewrite this over here. So what is this blue region? This blue region is just, you're integrating the Gaussian density over this is just the thing in these curly braces is precisely the blue region. It's the set of all points which are distance at most blah from k, okay? Let's just say k prime, but that's okay. So we can break this down into level sets. So I'm just doing a change of variables. It's going from t equals 0 to exactly this distance, integrating the Gaussian density along the boundary of each of these level sets. So kt is all the points which are distance at most t from k. And now this quantity is a very natural and well-studied quantity in convex geometry. It's just the Gaussian surface area. So if you didn't have the Gaussian density, this would just be the normal Euclidean surface area. But since we have the Gaussian density weighting this surface measure, it's just the Gaussian surface area, which I'm going to call GSA. And this is where we appeal to another big hammer from convex geometry, which tells you that if you have any convex set in n dimensions, then its Gaussian surface area is n to the 1/4. So this explains why we had that 1 over n to the 1/4 earlier. Again, here's just the definition of Gaussian surface area. Hopefully this is making sense. Good. So we just take this upper bound due to Keith Paul, and we plug it back in over here. And we get that you're integrating n to the 1/4 over an interval of width 0.05 times n to the minus 1/4. This is at most 0.05. Yeah? So adding up this 0.05 with the error we got by intersecting with the L2 ball, you get an error of 0.1, just triangle inequality. So this is how we just show this exponential upper bound. And even though it's kind of it ends up relying on like these two non-trivial technical results from convex geometry, but it's kind of a simple proof. Yeah? Any questions about this? Yeah. question. So you're asking why we're truncating it. I mean, it only helps you, yeah. I guess if you don't truncate and you do this level set business, this would maybe, it's a little annoying. I'm hiding one tiny thing under the rug. I can say more about this later, but it's kind of annoying. But truncation only helps you, yeah. Thanks, good question, good catch, yeah. Awesome. So, good. So this is the upper bound. The rest of the talk is going to be about lower bounds. Yeah. So for the next 30 minutes or so, I'll tell you about lower bounds for this approximation question. Good. So a natural guess would be just the L2 ball, like just the Euclidean ball, because if you want to write it down exactly, you need infinitely many half spaces. And indeed, this turns out to be the hard instance for every other distance metric for this approximation question. So this was, maybe the first thing. This was the first thing we thought of, and it's maybe the first thing that comes to most people's minds. And this is where, we tried proving a lower bound with our bare hands, but we kind of struggled. And so we turned to classical complexity theory, which is, proving lower bounds is what pays for the roof on top of complexity theorists' heads. Yeah. So there's a lot of ideas in Boolean function complexity where they try to prove lower bounds for various computational models. And I'm going to try to tell you a little bit about this. This might seem like a digression, but we'll tie it back to convex geometry in just a few minutes. So just as a reminder, a Boolean function is a function which maps bit strings to bits. And Boolean functions are monotone if flipping bits from 0 to 1 can only cause the value of the function to increase. Yeah, so I'm going to depict the Boolean hypercube with this diamond, and monotone subsets are monotone functions are subsets which, as you're walking up in Hamming weight, you never leave the set once you enter the set. Okay? So the pink region just corresponds to the input points which take value 1 under some monotone function. Good. So these are super well studied objects in complexity, in combinatorics, in property testing, learning theory, and we know a lot about these objects. But it turns out you can ask almost all of these questions for convex sets as well. And often the results turn out to be strikingly similar. So there's not only a qualitative correspondence, but there's also a quantitative correspondence between these two seemingly unrelated settings. And I spent a lot of time in grad school trying to work on kind of understanding this correspondence a bit better. And so there's kind of this weird analogy between convex subsets of Rn and monotone subsets of this Boolean hypercube. And let me give you a few examples of this. So maybe one really simple convex set you might think of is the slab. This is an intersection of two half spaces. Or in other words, it's just all the points such that the first coordinate is at most 1. So it's essentially a one-dimensional object. And this turns out to behave a lot like the Boolean function, which is a dictatorship, just a projection onto the first coordinate x1. Another natural set that we've been thinking about is the L2 ball. And the analog of the L2 ball turns out to be the majority function. So you take in n bits and you output the most popular bit. Yeah. And one way to think about it is as follows: like over Gaussian space, half of the Gaussian measure is, this set has Gaussian measure exactly 1/2 because, well, that's just how it works. And this is, you could think of the L2 ball as the inner half of Gaussian space. And you could think of majority as the top half of the Boolean hypercube. But if that seems hazy, that's OK. And another extremal kind of natural convex set is the L infinity ball, the cube. Again, we're scaling it so that the Gaussian measure is 1/2. This like goes back to Yu's point from earlier about what if the set is far away from the origin. And the analog of the L infinity ball turns out to be this function called the tribes function, which is an AND of a bunch of ORs. So just as a reminder, the AND function outputs 1 if all the input bits are 1. OR function outputs 1 if at least one of the input bits are 1. And in some sense, this is an intersection of roughly n orthogonal slabs. And this is, again, like an intersection of n over log n, so basically n disjoint orthogonal clauses. So more generally, this example kind of suggests that an intersection of half spaces behaves a lot like an AND of ORs. Yeah? So intersections of half spaces behave a little bit like depth to Boolean circuits. Yeah? And just to introduce language, I'm going to call an OR a clause, standard terminology. Right? So you can ask this approximation question, approximating convex sets by intersections of half spaces. You can ask a Boolean analog of this question, which is approximating Boolean functions by depth to AND of OR circuits. Yeah? These circuits are called CNFs, conjunctive normal forms. And it turns out that this question is actually super well studied in complexity. Yes, there's a question?
So the approximation is that the Boolean function f to output 1 if the point is in the set K?
There's no set K. Sorry, I'm confused. What's your question? Could you repeat that? Yeah.
Polytope approximation.
Yeah.
Do it as an approximation on the CNF. What I'm asking is, since you're trying to learn this set K in higher dimension, that's the definition of multiple hyperplane.
Uh-huh.
I'm asking, basically, it's going to boil down to taking a point in the high dimension and then viewing it.
Oh, I guess you're asking how to go from this setting to this setting.
Yeah.
Good. We don't know. We've tried a lot. It's kind of a hazy analogy, and like things kind of work out. But ideally, it'd be awesome if someone could prove like an invariance principle or something, which is like someone walks up to you with a Boolean function and you can write down a convex set, or vice versa. But we don't know how to do this. We just it's like guesswork, and like you fail and then you stand up and try again. Yeah. Sorry. This applies to all the Boolean functions, yes, yeah. But this correspondence is really for monotone functions. I can say more about this afterwards, yeah. Yeah. But no, that's a great thing. We tried for a while to make this correspondence clear, but so far it's just kind of hazy, yeah. Good. So all of you know what polytope approximation means, but let me formally tell you what CNF approximation is. So over here, approximation is going to be under the uniform distribution. So someone walks up to you with a Boolean function. How many clauses do you need to approximate the Boolean function f to accuracy 0.1? And the error metric is the exactly analogous. You just take the uniform distribution over the cube, and you look at the fraction of the error region. You look at the probability of landing in the error region of these two functions. Okay. And again, just as a reminder, clauses are like ORs. And so coming back to polytope approximation, we thought that the L2 ball would be extremal. And the analogy kind of tells you that the L2 ball behaves a lot like majority. So it's natural to look at lower bounds people have proved for the majority function for CNF approximation. Yeah. And it turns out that things are known over here. So before I tell you about the result, it kind of relies on one definition, which is a really cool definition if you haven't seen it before. So given a Boolean function, there's this quantity called the total influence of the function, which tells you, on average, how many directions matter for the function. So given an input point x, you can flip n coordinates and see if the value of the function changes. So this tells you how many of the directions matter at a point x. And if you take the average of this quantity, you get this thing called the total influence. It's a very natural isoperimetric notion, and if you think of the Boolean hypercube as a graph, it kind of shows up in social choice and economics. Kind of had its origins in voting theory, and it's kind of used everywhere in Fourier analysis now. And there's a really nice line of work starting with this cool paper of Kahn-Kalai and Lineal built around this notion of influence. And as kind of a fun exercise, does anyone want to guess what the influence of majority is? So it's going to be a number, but you're basically right. So all the points in majority which count towards this are the points on this line, like you said. So you want to ask the probability of landing on that line, which, yeah? It's 1 over square root of n times, yeah, but you're right. So I'm going to put words in your mouth, and I'm going to tell you what he's thinking. He's saying that the probability of landing in this middle region is the middle binomial coefficient, which by Stirling's approximation is just 1 over root n times 2 to the n. Okay, so the inference of majority is root n. Yeah. So it's just the probability of landing in this line on the boundary. Good. So so we're going to use this notion of influence to prove lower bounds for CNF approximation. So there's this nice result of Hostad and Bopanna from '97, which tells you that given any CNF with S clauses, the total influence is on the order of log S. And you can extend this to like higher depths, not just depth 2, but all we're going to need is this depth 2 result. So if you take this result and you combine it with the fact from the previous slide that the total influence of majority is square root n, it tells you that any 0.1 approximator needs 2 to the root n clauses. Yeah, so let's say G approximates majority, then essentially the idea is that the influence of G is close to the influence of majority, which is root n. So log S is lower bounded by root n. Just exponentiate on both sides. 2 to the root n is the lower bound on S. Yeah? But again, Fourier and monotonicity is behind the scenes. You really have to show that if G approximates majority, then the influences line up. Good. So we want to execute the same strategy in the Boolean, in this convex setting. But in order to do this, we need a notion of influence. And thankfully, a few years ago, my co-authors and I stumbled upon this notion of influence for convex sets in kind of a completely different setting. And so I'm not going to tell you what this notion of influence is, but it turns out to line up with exactly what we need, what happens in the Boolean setting. So you can follow the exact same recipe. So we have this notion of influence. The value turns out to be root n for the L2 ball. And we prove like this analog of this Hostad-Bopanna result for polytopes. And again, you kind of have to use convexity and some Fourier analysis to show that approximating the L2 ball needs 2 to the root n half spaces. Yeah? Is this making sense so far? Good. So just to summarize, we've shown that any convex set can be approximated with an exponential number of half spaces. And there's a lower bound for the L2 ball, which says that you need 2 to the root n half spaces to approximate it. But there's still a big gap over here between these two, between the upper bound and the lower bound. And you might think that by trying to do something smarter and not just copying the Boolean setting, you could boost this up to 2 to the root n. But let's see what happens for majority. So let's look at the analogy once again. It turns out that for the majority, there's an improved upper bound for the CNF approximation, which was proved kind of recently. So there's this really nice paper by O'Donnell and Wimmer. It's titled Approximation by DNF, but you could pretend the D is a C. That's OK. And they show that for any constant, for us epsilon's 0.1, there's a CNF of size 2 to the root n that approximates majority. It's a non-trivial probabilistic construction. So just repeating what they said in larger font, there exists a sub-exponential size approximator for majority. And their approximator is the following. They essentially put down 2 to the root n clauses, which are chosen uniformly at random. And the width of each clause is root n. And kind of a probabilistic analysis tells you that, one of that on average, the error of a function drawn as follows is at most 0.1. So just this tells you that in the support of this distribution, there is some function which approximates majority. So it's a probabilistic method type of argument. Yeah? Is this making sense? Yes, they don't construct it. Yeah, it's existential. It's not constructive. Yeah. Good point. Good. And so you can copy or like mimic the strategy once again. This root n becomes n to the 3 quarters for some annoying reasons. But the idea is the same. You take the L2 ball and you put down half spaces at random at distance roughly n to the 1/4 from the origin, and you intersect 2 to the root n of them. A different analysis will tell you that this error region in expectation will be at most 0.1. So the analogy kind of told us what the construction to try to analyze is, but the analysis is completely different. And this is something that happens a lot in this Boolean convex analogy as well. Good. So it turns out that the L2 ball is not extremal for this polytope approximation problem. And this is already kind of weird because the L2 ball is extremal for all the other distance metrics. So maybe it is extremal and there's a better upper bound, which would be super cool. But for a while we were pessimists, and we were trying to look for sets which are hard to approximate. So let's go back to this paper of Ryan O'Donnell and Carl Wimmer. If you keep reading the abstract, you'll see that they actually prove an exponential lower bound in this paper. So over here, they're saying that there's some monotone function. Like that's already exciting because the analogy is between monotone functions and convex sets. Monotone function, you can ignore this influence stuff. 0.01 approximated f needs size 2 to the n over log n. So log n doesn't matter. They prove a basically exponential lower bound. And the function they use is a really simple, really cool function, which I've already shown you. So, and I just want to say that the key idea behind this O'Donnell-Wimmer result was this technique of random projections, generalizing like classical random restrictions. And this was used in like this really awesome paper from 2015 proving an average case depth hierarchy theorem. So if you're interested in complexity, you can go take a look at this. It's a really nice result in my opinion. But anyway, the function that they use to prove this lower bound, the function that they show is hard for CNF approximation, is just this tribes function. So it's an OR of a bunch of disjoint ANDs. And what they show is that 0.1 approximations to this function need an exponential number of clauses. Yeah? Is this making sense? It should not be making sense because there's something slightly different. Tribes was an AND of ORs, but the hard function here is an OR of ANDs. So they're flipped. So the hard function is not CNF tribes, it's DNF tribes. So it's an OR of ANDs, but the parameters are the same. Okay? Hopefully I didn't lose people with that. Behind, yeah. So their results were like, so in the paper they do everything for CNF approximators of, DNF approximators of CNFs. So we switch the two. Yeah, in this paper, they're fixing CNFs and they're showing that DNF approximation by DNF is hard. So we're switching the two over here because we kind of are interested in approximating CNFs. Yeah. We're interested in approximation by CNFs, but this is the hard function. Okay. So it's an OR of a bunch of ANDs. But again, the analogy tells you how to go from an AND of ORs to a convex set, kind of. There's no precise connection, but it kind of tells you how to go from an AND of ORs to a convex set. And so we're going to try to go from an OR of ANDs to a convex set. It's DNF tribes. And there's a natural thing to try. So here's DNF tribes. CNF tribes is the function we kind of know how to think about. Again, the only difference is you have an AND on top here, this is OR over there, and OR here and there. These two are what are called Boolean duals of each other. Yeah. We know the analog of CNF tribes. It's this L infinity ball. And it's an intersection of roughly n orthogonal disjoint slabs. And there's a very well-studied notion of duality in convex geometry. You might have seen this when you learn linear programming duality, which tells you that the dual of the cube, or the L infinity ball, is the L1 ball. Yeah? So kind of the analogy is suggesting a very natural, hard set to approximate under the Gaussian distance. Yeah? Good. So natural conjecture, which we had, was that any approximator to the L1 ball must have 2 to the n half spaces. And this seems very reasonable. So here's the L1 ball in 3 dimensions. It's got 8 half spaces, right? 4 on top, 4 on the bottom. 8 is 2 to the power 3. You go in n dimensions, the L1 ball has 2 to the n half spaces. And our kind of intuition initially was that in order to approximate the L1 ball, you kind of have to get it right in each orthant in Rn. And there's 2 to the n orthants. So it might need 2 to the n half spaces. And we got super excited because we thought, we're going to come up with like this Gaussian version of random projections. And we spent roughly a year trying to prove this. And it turns out to be false. It turns out to be very much false. So we spent a year trying to prove something which was false. So that was a fun project. But it turns out that you could kind of use the ideas from this L2 ball approximator to get a sub-exponential complexity approximator to the L1 ball. I'm not going to go over the proof, but it's a probabilistic construction that's starkly different from the L2 ball construction. You essentially sample low-dimensional L1 balls, turn them into cylinders, and you intersect them. And here's kind of a cool tool, which I didn't know about until I worked on this problem. You kind of need to use multiplicative Gaussian tail bounds. Standard trickery like Gaussian concentration or like using a central limit theorem doesn't work because essentially you're dealing with, you're trying to get like Gaussian type tails when you're far out in the tail. And so when you use standard machinery, the error dominates over like the probability of the density of the point you're at. So you need multiplicative tail bounds, and they exist due to Petrov. I didn't know about them, and they're super useful, I think. So there's one technical takeaway from this talk. It's that these multiplicative Gaussian tail bounds exist, not just additive. Yeah? Okay. Is this making sense?
Anti-concentration is the concentration of measured mass.
Yeah, like we want to essentially say that there's not too much mass in a small region. Yeah, there's lots of mass outside a small region. Yeah, and hopefully I'm making sense when I'm saying additive versus multiplicative. You? Yeah.
What exactly is the sub-exponential? Like how many half spaces do you need to get there?
Good. So we need 2 to the n to the 3/4. The bottleneck is this multiplicative tail bound. If you can kind of improve it, you might be able to improve this to a root n. But in some sense, it's not worth doing, and I'll tell you why in just like 1 or 2 slides. But again, just to say one more thing about these bounds, additive bounds just tell you that if you, or actually maybe I'll say more later if people want to hear it, since I'm short on time. Good. So 2 to the n to the 3/4. And the same influence-based lower bound goes through. So you can show a 2 to the omega root n lower bound for the L1 ball. And it's natural to ask if you could do, sub-exponential facet complexity for LP balls, and not just the L1 norm or the L2 norm, but LP norm. And it turns out that this construction generalizes for P between 1 and 2. But it breaks at P equals 2 for a technical reason to do with these multiplicative tail bounds, which is why we kind of think there should be a different way, because as P goes to infinity, the problem should only get easier. The L infinity ball is the cube, which has n faces in Rn, like a linear number of faces. So the problem should get easier as n goes to infinity, but this proof doesn't really take advantage of that. So we kind of need to, it'd be nice to find a different way to do this. And there's more in this paper. We actually show some average case lower bounds, which are like correlation bounds in the Boolean world. There's connections to learning theory, weak learning lower bounds, and pseudo-randomness. But since I'm short on time, I'm not going to say much about it. But There's many open questions. So maybe something which I really like is, we don't know what the right answer is. Is it 2 to the n or is it 2 to the root n? This is a lucrative financial opportunity because my advisor will pay me $10 if there's a better upper bound and I'm willing to split it. Generalizing this LP ball construction is another natural thing. It might be like a good starting point for the bigger question. And another natural question is instead of thinking of the number of faces you need to approximate convex sets, you could think about the number of vertices you need, whose convex hull approximates the convex set, target set. So it's a natural alternative measure of complexity, and this is a little bit like approximation by DNF, as opposed to approximations by CNFs. And there's a bunch of other questions as well, but in the interest of time, I'm going to stop here. Thanks for listening. Yes.
I am trying to understand the intuition behind random sampling, let's say for the Boolean approximation to make it concrete. So, two related questions. If some oracle somehow gave you the approximation for dimension D, does that naturally lead to a deterministic method to give the approximation for either dimension D plus 1 or D minus 1?
Good question. I don't know. I don't think so. I don't know the answer to this. We tried thinking about this, but we don't know. Yeah.
And a related question is, the functions you're approximating have the property that they're symmetric.
Symmetric in what sense?
Well, like the tribes.
Tribes are symmetric. Yes, yeah. You can permute them and the function stays the same.
Right.
Yeah.
So can you prove that there's a best approximation that is also symmetric? That can be proven?
That's a good question. I don't know of a result of that sort. Yeah. So tribes needs an exponential size approximator. Maybe for majority, the Talleyrand function, like the random sampling thing, it is symmetric. So the approximator for majority turns out to be symmetric. And majority is symmetric. You permute the bits, the most popular bit does not change. But I don't know of a generic statement that tells you that approximators of symmetric functions are symmetric. Yeah, I don't know of a generic statement. Yeah. I think people have looked into CNF approximation when the function is monotone, or like the approximator has to be monotone, but I don't know of a result about symmetry. Yeah, good question. Yeah.
I have a question on the diagram to CNF or DNF.
Yeah.
I was wondering, so there you consider the unity distribution.
Yeah.
Where does it come up when you translate to Gaussian? Or like, does it make sense to ask the same question regarding Gaussian distribution there as well?
In some sense, like you could think of the cube as a generalization of Gaussian space. Because if you have the cube, if you add up a bunch of bits and rescale, you get the Gaussian distribution. So all of Gaussian space is kind of a special case of the Boolean hypercube. And people use this result. Like oftentimes in Boolean function complexity, when you want to prove things, you sometimes prove it for a Gaussian special case. Then you try to generalize it to the Boolean setting. So yeah. You should think of Gaussian as a special case of Boolean. Yeah. There was a question over there. Yeah.
Does one actually give a little bit more intuition of complex setting identity?
And Boolean functions.
It seems like your problem looks like it was a clear match.
Oh. Yeah. Well, I apologize if it seemed like there's a clear mapping because it's actually a very hazy mapping for us. But I'm glad it seemed clear. Sorry, I'm trying to pull up a slide. Yeah, these. We don't know of a clear correspondence. Like we would love one, but in some sense, I don't know if there is going to be one because you come up to me with a monotone Boolean function. I just don't know how to write down a convex set. In Boolean function complexity, people sometimes prove things by viewing it as a function over Rn. like extending monotone functions to monotone functions on Rn somehow. But this analogy kind of loses. Like it doesn't work for this analogy. And in some sense, like almost all of these proofs are different between the two settings. Like the results turn out to be the same. You know, the statements are the same. The quantitative bounds turn out to be the same, but the techniques used are completely different. So just as a simple example, this Harris-Kleitman inequality was something known since like the 50s or 60s, and the proof is 3 lines long. And the analog of that is this Royens correlation inequality. It was open for 75 years. The proof is not easy. It was proved in 2014. But the statements are the same, and the techniques used are completely different. So we're still trying to understand this analogy better. But it's been a really good source of questions in the convex setting. And oftentimes it gives back to the Boolean setting as well. So like some of this work I did on convex influences led to new stuff in the Boolean setting. But we don't we don't fully understand the analogy, so I'm happy to talk more about it, but it is kind of hazy, yeah. Like often, like, you know, when I give you these examples of functions and sets, oftentimes some Boolean function is extremal for some inequality, and another Boolean function, and a convex set turns out to be extremal for the analog of that inequality. And then like you kind of, in hindsight, you're like, oh yeah, these two are kind of like each other. But we don't have a principled way of going from one setting to the other. Yeah. Soren, yeah.
You mentioned the influence measure has a connection with voting theory.
Yeah, yeah.
Is it studied by mathematical economists?
Yeah, it's called the Banzhaf power index in voting theory. Yeah, yeah.
It was very pleasing to see you using voting theory.
Yeah, yeah. Yeah, it like originated from like econ and people trying to think about voting schemes.
All right, cool.
Thanks, yeah.